In module 3.4, we worked examples of expectation and variance of simple functions. And we chose the example of bending of a beam as well as the interference in a bearing between the housing and the shaft. In 3.5, we're going to derive a couple of formulae that have importance to sample selection later on. And also another common formula that you will see for standard deviation, sample standard deviation, that might seem confusing as to why the formula seems different from what we have discussed so far. So I'm going to discuss 2 points here. So let's start with the first one, which is sample mean variance. So we know that if I take samples out of a large population, let's say I have 1,000 items and I take samples of 100 items at a time, each sample is going to have a different mean value. Now you could take a more extreme sample, and you could take a sample size of only 10 items out of 1,000, 10 at a time out of 1,000, and you're going to see a lot more variability in terms of the mean of the sample because the sample size is not large enough. So what is the sample mean itself statistically distributed? And the answer is yes, it is statistically distributed. And it's also a distribution whose mean value and variance we can estimate. And that's what we will do here. So it turns out if you have samples of population and they have statistically distributed mean values, the mean values of sample means, that is, the sample mean is denoted by x bar, and the mean value, the expected value of x bar, is mu, which is the population mean. And similarly, the variance of the sample means, which is the distribution of these sample means, is denoted by sigma sub x bar squared, and that's sigma squared over n. And sigma here is the population standard deviation. We will try as far as possible to not use this sigma notation for standard deviation. We'll try to use S for standard deviation, but since it's common to use sigma for population standard deviation, we will use that wherever we have to refer to population standard deviation, as in this particular statement here. So the sigma x bar quantity here, sigma x bar is what is defined as standard error. And what it says is the variability, the variance in the mean value of my sample will depend on 1 over n, n being the sample size. As my sample size becomes larger and larger, the variance in the mean value x bar starts to go down. And so therefore the standard error is important in determining the number of samples that one needs to have. So larger the sample size. In general, larger the sample size, less the error. Okay, so let's go through and derive this. It's a fairly simple derivation, so let's go through and derive this. Okay, so what we want is, we know that x bar is defined, let's assume equal probability of my observations, or so x bar is defined as 1 over n summation over I going from 1 to n of xi. Okay. So xi, or here what we are assuming is xi are equally, have equal probability, or equally possible. And the other thing that we're going to say is xi, all these observations xi have expected value of xi, we're going to say is mu, which is the population mean. Now, the observations vary, but the expected value of that observation is the population mean. And x bar is the sample mean. So now I can ask the question, what is the expected value if the expected value of each observation is mu? What is the expected value of the sample mean? And that's nothing but the expected value of 1 over n times summation I going from 1 to n of xi. And we know from the definition of expected value that the expectation of a sum is sum of expectations, and the constant times expected value of a constant times a random quantity is equal to constant times the expected value of the random quantities. So I'm going to write this as 1 over n summation. I'm going to do one step at a time. 1 over n expected value of summation I going from 1 to n of xi. And now I will use the property of expected value, that expected value of sum is sum of expected values. So I going from 1 to n, and this is expected value of xi, which is 1 over n summation I going from 1 to n of mu, which is the population mean, and that's equal to mu, because n times mu divided by n gives you mu. That's the expected value of the sample mean. So in other words, if I have lots and lots of observations, each observation, if I have infinite number of observations, each observation will have an expected mean value of the population mean, which is mu, and therefore my sample of n items out of this large population will have a mean value of mu as well. So now we can go on and estimate the variance of the sample mean, and the variance in using the same logic as above. So the variance of sample mean, and sample mean is defined as 1 over n summation I going from 1 to n of xi. And again, using what we know about expected value of a variance of a constant times a quantity is being 1 over the constant squared times variance of the quantity. And we also know that variance of sum is sum of variance, because variance is integral, or in this particular case is summation of xi minus xi bar squared. So it's, so the variance will, this sum will be 1 over n squared times summation I going from 1 to n of variance of xi. And this in turn, now what we're going to say is that variance of each xi is equal to sigma squared, which is the population variance. And therefore, this is equal to sigma squared. And this in turn gives us the expression that we seek, which is sigma squared over n. So the key, again, assumption here is if I have lots and lots of observation x sub I, and ask the question, what is the variance of these observations? The variance of these observations will be the variance of the population. Okay. Each individual observation, because there are many of them, we're going to make the variance of that individual observations would be the population variance. That's sigma squared. So that's the standard. This is variance of x bar, and as we defined, variance of x bar is sigma sub x bar, which is defined as standard error. Sigma sub x bar is standard error. And this is an important concept. Let's go on to the next concept. The next concept is what is the estimate of population variance? Given that we have a sample, and the sample has this little n number of observations, and what we would like to do is to use this sample to estimate the variance of the population. We don't have a clear idea what the population variance is, and we actually don't know what the population mean is also. Of what we are trying to do is to estimate the population mean and population standard deviation. And in the previous slide, we saw how we could estimate the population mean. If I take every sample mean, that sample mean, the expected value of that sample mean would be equal to the population mean. And the variance of sample mean we saw was equal to sigma squared population variance divided by n. Okay. So now we are going to extend that idea to try to estimate the population variance. And the logic is very similar to what we did in estimating sample mean variance. So let's start with our definition of population variance and our definition of sample variance. So let's assume that population size is cap n, and let's assume that sample size is little n. Sample size is little n and population size is cap n. So by definition, sigma squared is 1 over n. This is the definition. Summation I going from 1 to cap n of xi minus xi or x bar squared. And this is the population variance. Now the sample variance is s sub x squared, and that is 1 over little n, I going from 1 to n, xi, and this will be this will be mu, okay, and this will be xi minus x bar squared. Okay, this is the sample variance. So what we would like to estimate is what we know the sample variance will depend on the particular sample that we choose. And if I choose multiple samples, each sample will give me a different sample variance. Therefore, the sample variance itself is statistically distributed. And this x bar is also statistically distributed. So I can write this as summation I going from 1 to n xi minus summation 1 over n summation j going from 1 to little n of xj, this whole thing squared. Okay, so that's my sample variance. So now I can ask the question, what is the expected value of this sample variance? Because I know this is going to be statistically distributed because n is smaller than cap n. So depending on the sample I choose, I'm going to get different variance and different mean values. But I do know the expected value of each xj would correspond to the population mean. So, and I'm going to use that fact here, okay, as we did in the previous derivation. So now I can write this as expected value of 1 over n summation I going from 1 to n xi minus 1 over n summation j going from 1 to n xj, and this whole squared. Okay. And the first step in working through this derivation is to expand the quantities within the parentheses, and notice that sum of expected values, and also use the fact that sum of expected values is some expected value of a sum is sum or equal to sum of expected values. Expected value of a constant times a quantity is constant times the expected value of the quantity. So I'm going to write this as 1 over n summation I going from 1 to n expected value of this quantity, which is xi minus 1 over n summation j going from 1 to n xj whole squared. So now I can go ahead and expand the square term inside the expected value. So I can write this as 1 over n summation I going from 1 to n expected value of xi squared minus 2 by n times xi times summation j going from 1 to n xj plus 1 over n squared summation j going from 1 to n xj times now xj summation times another xj will confuse the indices. So I'm going to call this as k. So I'm going to k going from 1 to n xk, and this is the expectation that I seek, and I can write this as 1 over n. Now again I can move I going from 1 to n, so I can now move the expectation of the sum is sum of the expectation, so I can move the expectation operation inside. So I can write this as expected value of xi squared minus 2 by n times summation j going from 1 to n expected value of xi xj. Okay, I'm using properties of expected value to write this expression, plus 1 over n squared summation over j 1 to n summation over k xj expected value of xj xk. Okay, so now what we are going to do is we are going to try to take out the common terms here. For instance, if I is equal to j, then I will have in the second term, I will have expected value of I squared. So I can take out that I squared term and treat that separately. And the same way, when j is equal to k, then I'm going to have expected value of j squared there. So now I can treat that separately. So I'm going to take those terms and treat them separately. So I'm going to go I equal to 1 to n expected value of xi squared minus 2 over n summation j not equal to I. So I'm going to take out the I term. Okay, so I should maybe take that out and write that first. So I'm going to write this as 2 over n expected value of xi squared minus 2 over n summation j not equal to I going up to n expected value of xi xj. And similarly, the next term I'm going to write as plus 1 over n squared, okay, plus 1 over n squared summation k j going from 1 to n of expected value of xj squared plus the last term, which is 1 over n squared, okay, and summation j going from 1 to n, summation k not equal to j going up to n, expected value of xj xk. Okay, so now we can use some observations that we've seen so far. We know that expected value of xi squared we can write as, if we know that the expected value of xi is mu, so recall this, and what we're going to say is that all observations xi, xj, etc. are independent, and each of them have a mean value, expected mean value to be the population mean. And recall also that variance of xi is sigma squared. Okay, by using the same logic, if xi and xj are independent, the observations are independent observations, then expected value of xi xj, which we know from our product formula, is expected value of xi times expected value of xj, which we can write as mu squared. And also the expected value of xi squared is the same as mu squared plus sigma squared. Recall expected value of x squared is equal to mu squared plus sigma squared. So we're going to say expected value of xi squared is mu squared plus sigma squared, given the property of expected value of xi, and the variance of xi. Okay, so now we can substitute all of this into our expression, and our expression becomes, so the expression that we have here, this expression becomes now 1 over n summation I going from 1 to n. And so the first term is expected value of x squared, so I can write that as mu squared plus sigma squared. Okay, and the second term is minus 2 over n expected value of x squared, so that together I can write as minus 2 over n mu squared plus sigma squared. Okay, and the third term is minus 2 over n summation j not equal to I expected value of xi xj, which I can write as minus 2 over n summation j not equal to I going up to n expected value of xi xj, which I can write as mu squared, and the next term is plus 1 over n squared, j going from 1 to n of expected value of, so summation j going from 1 to n expected value of xj squared, which is again mu squared plus sigma squared, and the last term is 1 over n squared summation j going from 1 to n summation k not equal to j going up to value of n, and this expected value of xi xj, which I can write as mu squared, expected value of xi xj xk, which I can write as mu squared. And you go ahead and simplify all this, and when you simplify all this, you should get n minus 1 over n times sigma squared. The mu drops out, and you get, this is the expected value of S sub x squared is n minus 1 over n times sigma squared. And what this means is that our estimate of the our variance from that we calculated from sample differs from the variance that we calculate that you would have from the population by this n minus 1 by n factor. So this is really what we would call as a bias in our estimate. So to correct the bias, so what we would need to do is to write sigma squared as n over n minus 1 times S sub x squared. Okay, and that would give us the formula n over n minus 1 times 1 over n times summation I going from 1 to n xi minus x bar squared. So you cancel out the n's, and that gives us the formula for estimate of population variance given a sample. So notice the 1 over n minus 1 in the denominator, and that comes about to correct the bias that we would have in our sample variance. Okay, so I'm going to stop this module here. And these are more intended to give you how we can apply what we have learned in terms of expectation and variance. Okay. And in next, we will switch to a new topic, and that's normal distribution. So we'll stop here.